Part 2 of net change theorem. Let's go ahead and jump right in with an example. This one actually should be relatively straightforward. We'll do one of these. We'll do one that's a little bit, it's different from particle motion, and then we will finish up with an example of how we deal with both displacement and distance traveled when we have a velocity function or a rate function that actually changes sign within the interval that is designated. This says, find the displacement of a particle moving in a straight line with a velocity of 4t minus 3 meters per second over the time interval 2 to 5. Now, this velocity function actually does change sign. It just doesn't change sign within the interval. Okay? This, of course, changes sign at 3/4. T is equal to 3/4. Well, 3/4 is not inside 2 to 5. Okay? So let's go ahead and just do the integral from 2 to 5 of 4t minus 3 dt. Okay? And what happens here is we just very simply 2t squared minus 3t from 2 to 5. Well, that winds up being 50 minus 15 minus 8 minus 6. Okay, this is obviously the position function, or this is v of 5 and this is v of 2. Remember, you don't know each one of these because you're not taking into account any constants, any vertical phase shifts. But you know that when you take the difference of these two, those vertical phase shifts, those constants would wind up falling out anyway. So here's what we have. We have 35 minus 2, so it's 33. Now, and like I said before, when we had another one, you can actually do this geometrically if you wanted, right? You know that it crosses over 2, 3, 4. It crosses over right here at 3/4, okay? And then from 2 to 5, you have it like that. So you could, do a triangle and a rectangle in terms of finding the area, or you could just go ahead and find the area of the trapezoid in order to find geometrically that it is indeed 33. Okay. Now that one, like I said, was relatively straightforward. Let's go ahead and do one that's just, it's not too difficult, but it actually winds up being a little bit more interesting, I think. Suppose a population of wild badgers is increasing at a rate of 100 plus t to the 2/3 badgers per year. Okay, so that's your rate function. Let's call it r of t. Okay, so you have, and I want to put it in descending order, so let's go ahead and do that. Okay. Badgers per year. Okay. Now, where t corresponds to the number of years after 2008, assuming the rate, meaning the rate function, doesn't change, by how much will the badger population increase from 2010 to 2012? Well, you know that 2010 is t is equal to 2. And you know that 2012 is t is equal to 4. So all it is just a little bit of translation work to actually take you to the integral 2 to 4 t to the 2/3 plus 100 dt. I know that that's going to be 3/5 t to the 5/3 plus 100 t from 2 to 4. Now, I'm not really looking forward to taking the cube root of 4, okay? And I'm hoping that nobody else is actually looking forward to that. So we'll go ahead and we'll actually plug it into our calculator. Now remember, in order to do an integral in your calculator, you just go alpha, F2. Number 4 right here is function integrate, okay? And we'll go 2 to 4 of x raised, and you can do a proper fraction within the exponent, or you can just do a slant fraction like I just did, plus 100, and then of course you want to do dx. Now that would be how much the badger population would increase in those 2 years. Now that doesn't tell you what the badger population is at 2010. It doesn't tell you what the badger population is at 2012. It merely tells you the net change in the number of badgers between 2010 and 2012. Now, of course, you don't actually have to do this on the home screen. If you actually went ahead and plugged this into your calculator in your Y1 for whatever reason, you actually would have that as Y1, and you could actually just go ahead and use that notation here on the home screen instead of actually plugging in the expression in here. You can go alpha F4 Y1, and it'll go ahead and actually pull this notation from your y equals screen, and you'll actually get the same exact thing. Okay, so if you're actually using the function for more than one thing, which on the AP exam come May you will be, because it'll give you a scenario and it'll ask you like 4 different questions about it. It's actually a better idea just to get into the habit of taking the function that you're given, plugging it into Y1, and then if you integrate on the home screen, just doing it like this. Okay, and so we just take the number from our home screen, and it's 204.143 badgers. Okay, and of course then you just have to determine, you're just going to go, well, that, and then of course usually when you're dealing with living entities you always round up to the next number, so about 205 badgers. Remember that when you're dealing with this, you're going to want to show the decimal approximation to 3 decimal places, and then you're going to want to explain, why you rounded up to 205. Okay. Let's go ahead and let's do the problem where the velocity changes sign. It's actually in your book. I'm going to go ahead and pull it from the chapter review, number 56. And I hope you can see that. If I actually move it any closer, it tends to blur. A particle moves along a line with velocity function v of t is equal to t squared minus t. Now obviously that has zeros at 0 and 1. You can factor very easily to figure that out. Where v is measured in meters per second. Find A, the displacement, and B, the distance traveled by the particle during the time interval 0 to 5. Okay? Now I'm going to go ahead and recreate this right here. We know that v of t is equal to t squared minus t. Now I'm going to go ahead and plug that in, and we're going to talk about, let's go ahead and pull up Grapher. I think that's probably a little bit better since, so x squared minus x. And we'll go ahead and drag that into a position where we can actually see it. Okay. And we'll zoom out just a little bit, and so we can, we're not quite going to actually see where it is at 5, the output at 5, but you get it. From 0 to 1, you see that the integral is going to collect negative area, okay? So this negative area from 0 to 1 is actually going to cancel out with the first little bit of positive area right here. And that's why the integral from 0 to 5 will give you displacement, but because some of the movement was negative and some of the movement was positive, the integral from 0 to 5 is not going to give you total distance. Okay? Now, you know that v of t is going to be positive for t is greater than 1. You know that v of t is going to be negative, okay, for 0 to 1. Okay, well here's the thing. If I want displacement on 0 to 5, and that is the interval that we were actually given, it's very easy. Displacement is just the straight up integral, right? Displacement is the net change. So we'll do t squared minus t dt, and that winds up being 1/3 t cubed minus 1/2 t squared from 0 to 5. The great thing about having zeros, one of the limits of integration, is I don't have to plug it in, right? Because it's going to make 0. So I'm going to get 125 over 3 minus 25 halves, and of course you can get a common denominator, or just go ahead and actually find that. Something over 6, obviously. And it's a little bit late for me to be actually doing that in my head, so I'm going to go ahead and cheat, and it winds up being, okay, that winds up being 175 over 6, okay? Now, and that, of course, is approximately 29.167, okay? Now that is the displacement. But if I want the total distance, because basically this thing went a little bit negative and then went way positive, right? The 29.167 is basically from here to here, but it doesn't take into account the overlap right here. So my total distance should be a larger number. Now I know that from 0 to 1, it's going to accumulate negative area, okay? So what I'm going to do is I'm going to integrate from 0 to 1, the same t squared minus t dt. But I know that that's going to give me a negative. So I'm going to go ahead and plop a negative out in front to sort of unnegativize the negative. And then I'm going to go from 1 to 5 of t squared minus t dt. Okay? Now let's go ahead and let's do it with our calculator so that we save it just a little bit of time, since, you know, on these videos time is of the essence, and I don't think y'all really want to watch me do arithmetic. So we know that if we have negative integral from 0 to 1 of y1 dx, and then I add to it the integral from 1 to 5 of y1 dx, I'm going to get 29.5. Like I said, it was just a small overlap. So it's the difference between 29 and 1/6 and 29 and 1/2, okay? Because that really was a small piece of area between 0 and 1. So that's basically how it's done in terms of finding the total distance, okay? You basically find the interval where the velocity is going to accumulate negative area. You set up an integral for that interval, and then you just negativize it to sort of turn the negative back positive, and you add it to the interval that gives you positive accumulation of area underneath the curve. Now, some of you who are really clever, like, yeah, I'm not going to do that. I'm just going to go ahead and define y1 as the absolute value of x squared minus x, because I know that that's just going to take care of it. That's going to take that little dip underneath the x-axis, and it's going to bounce it back positive, and then I'm just going to go ahead and go 0 to 5 of the absolute value of x squared minus x dx, and that's going to give me the correct answer. And if you're thinking that, kudos, okay? That's actually very, very clever. Unfortunately, too many calculus teachers taught their students to do that, and therefore it is now disallowed most times on the AP exam. In fact, the instructions on the problem will specifically state, without using absolute value, find the total distance. And if you got your heart set on using absolute value, you're going to be very, very disappointed. Okay, so it's better just to learn how to do it this way. Okay. That kind of brings us to the end of the problems that I wanted to go over. I think that should be sufficient. If you don't find that to be sufficient for your needs in terms of the net change theorem, please do shoot me an email. I'll be happy to do 1 or 2 more videos. I just don't want to throw a whole bunch of videos up there that overwhelm you. Like I said, please do send any emails or concerns, questions, queries, stuff like that to me by email, and I will attend to them as fast as I can. Be on the lookout for videos on 5.5 if indeed we're going to be covering that before Christmas. If not, look for those videos in January. Bye.